Hey everybody, so continuing the topic of trusses. Previously we were analyzing trusses that were planar, so in a two-dimensional plane, and that each of the joints, we're considering them to be pins, so no torques at any of the joints. Now we're expanding our discussion to what is called a space truss. It's just a three-dimensional version, so we're no longer in a plane. And instead of pins, all the joints are ball and socket, the 3D analog to a pin. And we can just use the same methods, method of joints, method of sections. The technique is the same. It's just that the math is messier because now it's 3D. That's all. Okay, so for example, for this truss, space truss, if we have roller supports at B, C, and D, and a load up at A, we could use the method of joints. So for joint A, you draw the free body diagram like this. So let's see, let me label these. And there's that 1,200 pound load. Okay, and then we can sum forces and decompose into X, Y, and Z components. All right, so you can write basically three equations for how many unknowns? 1, 2, 3. 3 equations, 3 unknowns, which means you can solve for all 3 of these. And then you go to the next joint, say joint B, draw the free body diagram. Okay, so let me label these. Okay, and then there's this roller support. I'll just call it B. Y. It's only in the Y direction, right? Because it's normal to the ground. And notice that we already have this answer here, which is right here. So that means we have 1, 2, 3 unknowns, and we can write 3 equations. Right? So that means we know all 3 of these unknowns. And then you go to the next joint. So let's say joint C. Draw the free body diagram. And there's the roller support at C. I'll just call it CY. Okay, and now notice this is the same as this. Also, this is the same as this, which means there are actually just 2 unknowns left, and we can write as many as 3 equations. We don't even need all 3. Right? We just need 2 of them. And then we go to the last joint, joint D. So I'll draw the free body diagram for joint D. So let me label these. And then there's the roller support at D. But then notice this is the same as this. This is the same as this. This is the same as this, which means there's only 1 unknown left, this one, and we can write as many as 3 equations. We don't need all 3, we just need 1 of them. Right? And then that's the method of joints. You can solve everything everywhere, and it's very systematic. You just go joint to joint. For each joint, you can write 3 equations, and it always works. Okay, so as an option, let's go back to the beginning. So let's say we wanted to specifically solve for these 3 axial forces, which is here, here, and here. So that means joint D. So joint D, let me just draw it again. Draw it bigger. Okay, and then there's the roller support. And I'll label these. Okay, so we have 4 unknowns, but we could have, as an option, considered the entire structure. Like, we don't care about the members. All we care is that there's a load here and reactions at these 3 supports, that's a B, right? So B, C, D. Okay, so for the whole structure, and then we can write equations for the structure, some torque about anywhere we want. Okay, let me take a look at that original drawing. Let me rearrange a little bit. Okay, so in the x direction, we still need to break down let's see. Let's do this first. So in the x direction, here, there is nothing happening. Okay, so that equation doesn't help us. In the y direction, we have these 4 forces. In the z direction, nothing is happening. Okay, so neither of these equations really contribute anything. And then let's sum torque about wherever we want. So let me go where I have more space. So let's sum torque about over here, the origin at B. Okay, so then from B to C, cross this CY plus the torque from B to D cross this force plus from B to A cross this force. I'll just call it the load. Okay, so the sum torque equals 0. Okay, so let me just plug in the numbers so you can take a look at it. Okay, so from B to C, that's 606. And then cross CY, which only has a J component, plus from B to D, so that's 1000, cross DY, which only has a J component, plus from B to A, 532, and then the load was negative 1200 J. Okay, and then you just multiply this through, so let's just do this right. So I direction, negative 6CY I, and then J direction 0, K direction 6CY. Okay, now this one in the I direction 0, okay, J direction 0, K direction 10 dy. All right, and then here I direction negative of negative 2400, so plus 2400, J 0, K negative 6000. Equals 0. 0 means 0i, 0j, 0k. In other words, you just take the x components right here, negative 6cy plus 2400, right? I equals 0i. In other words, the x component of the torque equals 0. So this is one equation. And then let's take the j component, so there are none, okay? So, and then the z components, we got 6 cy, 10 dy, minus 6000. So this is in the k direction equals 0. So we have these two equations and this one over here. Right, so we have 1, 2, 3 equations for 3 unknowns. For the 3 unknowns by, cy, dy, the reactions at the three roller supports. Okay, I mean, practically, right? Just solve this for cy, plug that number in right here, solve for dy, then take cy and dy, plug it in right here, and then solve for by. Then you have all three. Okay, so then now that we have that, let's go back to our free body diagram here. So now we just need, right, we write these three equations for three unknowns, these three unknowns. But let's just break down these three vectors. So for example, vector T, A, D. We don't know the magnitude. I'll call the magnitude this. But the direction we know from A to D. Actually, it's going this way. So actually it's going from D to A. So the direction, we want the unit vector from D to A. And no problem, right? The unit vector from D to A is 5 minus 10, I, 3 minus 0, J, 2 minus 0, K. And then just divide by its own magnitude. Right? And then you do the same for vector, let's see, B, D. The magnitude, we don't know, but the direction is from D to B. So the unit vector from D to B. No problem. Right, from D to B, 0 minus 10, 0 minus 0j, 0 minus 0k. So in other words, the unit vector is in the negative I direction. Okay, and then we might as well just finish. All right, so the last one, from the vector CD, unknown magnitude, and the direction is from D to C. So we want the unit vector from D to C. Unknown magnitude, but the direction, no problem. C, 6 minus 10, I, 0 minus 0, J, 6 minus 0, K. Divide by its own magnitude. Right, so we have each of those vectors split up into XYZ components. So now we can write these, right? The X components. So the X component of AD is TAD minus 5 over that thing. 5 squared, 3 squared, 2 squared. Right, and the X component of BD is negative 1. And then the X component of CD, minus 4 over TCD equals 0. Right, and then you do the same for Y, same for Z. So Y component, right here. 3 over square root of that thing. And then the Y component of this is nothing. The Y component of this is nothing. And then the Y component of this, which we solved earlier. Okay, and then Z, same like Z for this. TAD, 2 over that thing. The Z component of this is nothing, and then the Z component of this, 6 over that. Okay, so then you have, and again, this is known. These are the unknowns. Okay, so you have 3 equations, 3 unknowns. How would you solve them? Just look, right? Solve this first, since it only has the one unknown. Plug that in here, solve for this one, and then you have these two, solve for the last one. Okay, so then that's how you deal practically. So if you want to see more examples, just let me know in the forum. Other than that, I'll see you on the next video.